In this video, we continue our concepts discussion on thermochemistry. We've learned about energy, enthalpy, and heat and work during chemical transformations. Now we'll look at more detail on enthalpy. We'll look at calorimetry, which is used to measure the enthalpy or the internal energy of a system as it undergoes a chemical transformation. We'll tie this together with stoichiometry. We will look at Hess's law, which allows us to combine delta H values for different processes to get delta H values of unknown systems. And we'll look at standard enthalpies of reaction. We'll find that for those who are in engineering, you think about thermodynamic cycles. So Hess's law is very similar to that. So we left off last time, we said delta H was equal to delta E plus P delta V plus V delta P if a system remains at constant pressure and nearly or constant volume, then delta E is approximately equal to delta H. So the P delta V and the V delta P terms fall out. But in general, the heat for a process at constant pressure is equal to delta H. So delta H sub P is equal to Q sub P. That was our big conclusion. So that gives us some sort of feel for what this enthalpy is. What is enthalpy? Heat at constant pressure. Now, enthalpy and internal energy are approximately the same number for reactions that don't involve gases, for reactions in which the total amount of gas doesn't change, and for reactions where the gas can change, but Q sub P is much larger than P delta V. So delta H and delta E turn out to have very important relationships, and we can think of them in many chemical instances as being approximately equal to one another. They are different quantities, but their magnitudes can be approximately equal, and their units and their numerical values can be approximately equal as well. So we know enthalpy is heat at constant pressure, but for many chemical processes, enthalpy and internal energy are very close to one another. So now let's look at two different types of processes. In the first case, we're looking at methane reacting with oxygen going to CO2 plus water, and that's water vapor. What kind of a reaction is that? That should remind you back to chapter 4. That's a combustion reaction. It's a redox reaction. And in this case, it releases a lot of energy. We talked about methane before. Methane is the primary component of natural gas, and it's got a nice high enthalpy. So on this diagram now, notice we don't have energy on our vertical axis. We have enthalpy, that is H. And that's the parameter that we can measure precisely. So our initial enthalpy is high for methane plus oxygen. You ignite the methane and it burns and you get carbon dioxide and water. And the final enthalpy is lower. Heat flows out of the system. You burn natural gas, you get heat out. This is what we term an exothermic process. If delta H is negative, it is an exothermic process. Heat flows out of the system. On the right-hand side, we have the companion process. The opposite occurs. Here on the bottom, in the green box, is ice. That's solid water. It's got a low initial enthalpy. The final state of the system is liquid water. That's the brown box. That's a higher enthalpy. Heat has flowed in. Delta H is positive. This is what we term an endothermic process. Heat flows in an endothermic process. Delta H is positive. And delta H is negative, we call it exothermic. Delta H is positive, that's endothermic. That's something to remember. Delta H is an important parameter for a variety of different processes. Ones with which we're going to concern ourselves are phase changes and chemical reactions. There can be enthalpy changes that occur in engine cycles, in refrigeration cycles, in a variety of other sorts of transformations. We're going to focus most heavily on chemical reactions with some look at phase changes. This is a very general way to think about delta H. In general, if A goes to B, so A is reactant, B is product, delta H for the process is equal to HB minus HA. We take our final state minus our initial state. That tells you where we've gotten to. H depends on the type of material. So the composition of the material, what is A, what is B? The enthalpy of water is very different than the enthalpy of hydrogen, as you can imagine. It also depends on the amount of material. The more material you have, the more enthalpy you have, the larger the enthalpy value. So this can be in moles, or it could be in mass, it could be in grams or kilograms, and you know how to convert moles to kilograms or grams very readily. Finally, enthalpy depends on the conditions. Depends on the temperature, the solvent, electrolyte concentration. It can depend on other parameters of the system. We won't focus so much on the conditional dependence of H. You'll get that in later courses. We're going to focus primarily on number 1 and number 2, the composition of the material and the amount of material and how that changes what the enthalpy of our process will be. Now, here's an important point. And for some folks, it's a sticking point, but we just have to remember there's a simple solution for us. We don't know the absolute value of anything. We don't have enough information, and we don't have the data that's necessary. We can't relate the enthalpy to nothing. But what we can do is we can come up with a relative scale. We develop standards for enthalpies. And what we really concern ourselves with are enthalpy changes during processes anyway, so as long as we can tie our scale to some standard, our delta H values will be correct. And the standard for this system we set is for H equals 0 for an element in its most stable form at standard temperature and pressure. So we know old STP from chapter 5 for gas laws. We start to tie this into chapter 6. So delta H sub F superscript 0, that's what we call the standard enthalpy of formation. There are lots of government tables, companies all around the world, they use these. They're standard values. Everyone on Earth uses the same delta H sub F0 standards. So the standards are universal. Delta H sub F superscript 0 is the standard enthalpy of formation. What does this mean? The superscript 0 means we're looking two things. At standard conditions, STP, for molar quantities. So superscript 0, that tells you when we get a number for an enthalpy of formation, that tells you it's for a molar amount, for 1 mole of that substance at STP. Now the delta and the F are important because they tell us this is the process of formation of this substance from the elements. And we know, since it's a superscript 0, that's standard conditions for 1 mole of the material. So delta H sub F of H2 gas should be equal to 0. Since I'm forming an element from its element, there's no change. Delta H sub would be 0 for that process. So delta H of formation of hydrogen gas is 0. And remember, mercury is a liquid under standard conditions. So delta H of formation of mercury is 0 kilojoules. Notice these are all molar quantities, so they are per mole, so that defines how much material. For sodium, it would be sodium metal as a solid. That would have an enthalpy of formation of 0. So now, without knowing anything more, you know the enthalpy of formation of approximately 90 naturally occurring substances. All the elements at standard conditions, their enthalpy of formation is 0. Here's a very small table. There are literally many thousands of these values that have been generated, tens of thousands of numbers for enthalpies of formation, because these turn out to be very important numbers. They would tell you, how much energy you could derive from something if you put it into an engine or into a system. So these are selected standard enthalpies of formation. These are the delta H0 sub F values in kilojoules per mole. You notice all the elements, so calcium solid, chlorine gas, Cl2, the diatomic gas, N2 gas, O2 gas, they're all 0. The compounds very often are negative in their enthalpy of formation. What does that tell you? It tells you that those substances are more stable than the pure element. Some are positive, and those are for less stable systems. Let's take something really simple. Let's look at oxygen in this table. So under the title oxygen, we see O2 and O3. O2 gas is the normal oxygen gas. O3 gas is ozone. That's an allotropic form of the element oxygen. You notice that's 143 kilojoules per mole. That's at a higher enthalpy. That's a less stable system than normal oxygen, which makes sense under ambient conditions in the troposphere on Earth. Oxygen's the most stable form for O2 is the most stable form for oxygen, so molecular diatomic oxygen is its most stable state. Now we can go down lower. Water as a gas and water as a liquid, those are very negative values. In fact, those are very stable substances. Water is a very stable material. It's not particularly reactive. Very stable, very negative value. And you'll also notice that water gas is higher enthalpy than water liquid. It's a less negative value. And that makes sense because water gas would release heat to go down to water liquid. So you can take those two numbers and maybe relate that back to one of our earlier diagrams and see that steam going to water liquid should be a negative delta H value. There are a variety of types of delta H which are related to the delta H sub F zeros, the standard enthalpies of formation. And we'll look at just a few of them, the ones that we'll use for this course. Delta H sub M superscript 0 is the standard enthalpy of fusion. That is, fusion is melting. So if I take a substance as a solid and convert it to a liquid, that's typically going to require positive delta H for that transformation. Delta H sub M, and that will be delta H formation of A as a liquid minus delta H formation of A as a solid. There's a standard enthalpy of vaporization, that is boiling. So A in its liquid form going to A in its gaseous form, delta H sub 0 or superscript 0 vaporization is the enthalpy of formation of A as a gas minus the formation of A as a liquid. Finally, there's the enthalpy, a standard enthalpy of sublimation, that is going from the solid state directly to the gaseous state. And in that case, the sublimation enthalpy is equal to the enthalpy of formation of the gas minus the enthalpy of formation of the solid. And this occurs, for example, if you have ice cubes, you leave them in your freezer for too long, of course, they seem to shrink and get smaller. They're undergoing sublimation to the gaseous state. This slide provides very important information for you in thinking about enthalpy changes. This provides information on the standard enthalpy of reaction, and this can be generalized across all the processes that we're going to look at. What we've done is we've taken a prototype reaction. X moles of substance A plus Y moles of substance B goes to Z moles of substance C plus W moles of substance D. The standard enthalpy of this reaction for that reaction as written is going to be the enthalpy of formation of all the products minus the enthalpy of formation of all the reactants. How do we get the enthalpy of formation of the products? That's shown at the very bottom for the equation in bold. The enthalpy of formation of the products would be Z times the standard enthalpy of formation of C, since we have Z moles of that produced, plus W moles, W times the enthalpy of formation of D, since we have W moles of substance D. That term in brackets is equal to the enthalpy of formation of the products. Then we subtract off the enthalpy of formation of the reactants. That will be X times the standard enthalpy of formation of substance A plus Y times the standard enthalpy of formation of substance B. That term in the second bracket is the enthalpy of formation of the reactants. Notice we put the stoichiometric coefficients multiplied by all these standard enthalpy of formations. The way you'll handle this when we get to the mechanics section, you'll have to balance chemical reactions, which you now know how to do. You'll take those coefficients and you'll multiply by the delta H formation values. You will get those from a table. So those will all be known values that will be given to you. So you'll balance the equation, you'll take the tabulated values that you'll be given, you multiply them out in this equation, and that will give you the enthalpy, standard enthalpy for your reaction. Here's a specific type. It's the enthalpy of combustion. The standard enthalpy of a combustion reaction is given below. So here we've taken some substance CX plus C6Hy, which would be a typical hydrocarbon, reacts with oxygen to produce carbon dioxide and water. And if we notice down below, our products, we've written out X times the enthalpy of formation of carbon dioxide, Y over 2, enthalpy of formation of water. Make sure you use the right form of water as gas. So that first set of brackets is our products, minus the enthalpy of formation of the reactants. And notice we did not put in the enthalpy of formation of O2. Why not? Because it's 0. So we can leave that off. Now we're going to look at calorimetry. Calorimetry is the measure of heat flows during processes, and these are the source for all the delta H sub F superscript 0 values that are tabulated. And calorimetry is based on one simple type of equation, and that's shown here. The equation is Q equals Cp delta T. So let's look at it as the first equation. Q, and Q as we know is heat. Q, for any, if you look at something that undergoes a temperature change, Q is equal to Cp times delta T, and I've written that out explicitly as T final minus T initial. What is Cp? Cp is the heat capacity of the system that you're looking at. So that will tell you what its temperature change is. Now we can break this out more completely. Q is equal to m Cp bar times delta T, where m is the mass of the substance and Cp bar is the specific heat capacity. So there's a difference. Cp and Cp bar, they're both related to heat absorption. But Cp is a generalized heat capacity. You won't see those tabulated anywhere because they depend on how much of substance you're looking at. Cp bar is the specific heat capacity. So that's the intensive property. That's the one you'll see tabulated. So when something undergoes a temperature change, you can tell what the heat flow was. Because you know the temperature change, if you know the specific heat and the mass of substance, then you can figure out how much heat had to go into this to that system to cause that temperature change. So you can see now we can carry out chemical reactions, watch temperature changes. If we know heat capacities or specific heats and amounts of substances, we can deduce what Q values are. And if we do these at constant P, Q at constant P will tell us enthalpy. Now there are three terms that you'll see here, and you'll see these terms a lot. I think it's useful to write out the exact definitions, but we're going to focus on the first one. That is specific heat capacity. That's the one you're going to use. But the other two you'll see, and just it's important to use careful language here. Specific heat capacity is related to the energy required to raise 1 gram of a select type of matter by 1 degree. The specific heat capacity is the energy required to raise 1 gram of select matter by 1 degree. So it's going to be joule per gram Kelvin. The heat capacity would be for a particular system you're looking at. That's the energy required to raise a sample of matter by 1 degree. So you might have 15 grams of water, for example. So 15 times the specific heat capacity would give you the total heat capacity, or the heat capacity for the system. Now you'll also see a term specific heat thrown around. We won't use this, but you will see this. It's a unitless quantity. It's the ratio of the quantity of heat required to raise the temperature of the material by 1 degree to that required to raise the temperature of an equal mass of water 1 degree. So it's simply the unitless version. We'll use specific heat capacities. And here's a table with specific heat capacities of a variety of materials. You can see there's a bunch of elements. Typical values, these are listed in joule per gram Kelvin. So for metals, they're less than 1. They can be as low as a tenth, as high. For aluminum, it's high, 0.9. We'll see later on, there's in general chemistry 2, there's a law of Dulong-Petit, which allows you to relate the specific heat capacity to the atomic number of the system. We have some solid materials, some other substances here, wood, cement, glass, granite, steel. They're all relatively small numbers, but those are typical values around 1 or so. Down below we have compounds, and you'll notice the biggest number on here is water. Remember we mentioned this in chapter 4? Water had a huge capacity for absorbing and releasing heat. It's a great storehouse for energy, for thermal energy. These are numbers that you'll use in different sorts of experiments. Now, calorimetry is the experiment for measurement of heat flows during reactions using those equations we just looked at. Q equals mCp bar delta T. In this case, the system and a local surroundings are going to be isolated from the true surroundings. You're going to have an insulated system. It's like being in a thermos. So you'll have heat flow, but the heat flow will be contained inside a small region of space. Your system will be your chemical reaction. The local surroundings might be water for the solvent or a water bath around your chemical reaction. The system is the chemical reactants under study. The local surroundings are the material in thermal contact with the system, and they have to have a known heat capacity, C sub P, and it's usually a large number. And then we thermally insulate or isolate the system and its local surroundings from the true big surroundings. So here's, we're going to look at 2 types of calorimeters, and the first one is one that you'll use when you do general chemistry lab. This is what's called a coffee cup calorimeter or an open calorimeter. Here you have some sort of thermos. You can have styrofoam cups that you use as insulators. There are other sorts of kind of more advanced versions that don't just use styrofoam cups, that are a little more robust and don't break. And here we carry out a reaction, and this system has just simply got a cork stopper in, so since it's gently held on, this system is at constant pressure since it's exposed to the atmosphere. So here we carry out a reaction. Your sample down below is your system, and then you have your water around here. Water has a known specific heat. If you know the volume of water, you know the mass of water. If you know the mass of water times the specific heat, that gives you the total heat capacity. The thermometer measures the temperature change. If you know the temperature change and the water heat capacity, you know the heat flow. It turns out that this type of device measures enthalpy. That's heat at constant pressure because it is at constant pressure. Another type of system is called a bomb calorimeter. We in our lab and our company use this quite regularly. A bomb calorimeter is a system that is at constant pressure. So it's a constant volume. This is not at constant pressure. It's a constant volume system. And inside you have what's called a bomb. It's just a sealed metal container where you carry out your chemical reaction. So this is a device that measures heat at constant volume, Q sub V. This is one for directly measuring delta E. We know delta E and delta H can be close to one another, but they're measured slightly differently. So we'll do some example problems for calorimetry when we get to the mechanics lecture. We've talked about these types of enthalpy changes, enthalpy of combustion, enthalpy of formation, we know how that works, enthalpy of fusion, enthalpy of vaporization. Stoichiometry ties together very importantly because we know we have to have a balanced reaction based on a balanced chemical equation. We have to multiply the coefficients times all our standard enthalpies of formation. The sign of the overall delta H that we measure for a reaction is going to tell us whether it's exothermic or endothermic. If delta H is negative for the process, it's an exothermic process. If delta H is positive, it's an endothermic process. The magnitude or the size of delta H is proportional to the amount of substance, and it tells us how much total heat flows in this. The value of delta H can be used in calculation. Here we see a flow chart that reminds us back to chapter 3. It ties together amounts of substance A with amounts of substance B by the balanced chemical equation. We also know now that we can calculate a heat for this process. So we can get a delta H value for the A to B transition or the A to B transformation. If the system absorbs heat, then delta H is positive. It's an endothermic process. If heat is released, it's an exothermic process, and delta H is negative. Hess's law is something that's useful. Hess's law states the enthalpy change of an overall process is the sum of the enthalpy changes of its individual steps. So if we have a series of steps, delta H overall is delta H1 plus delta H2 and so on, up to delta H sub n. So we add up all of these. And that makes sense to us because enthalpy is a state function. So the overall change doesn't depend on how we do it, but it depends on what the individual steps, how they add together. And so delta H overall will simply be the sum of the individual steps. Delta H for an overall reaction can be calculated if delta H values for the individual steps are known. Another way to state this, and one that some engineers may find comforting or physicists, Hess's law can be stated as the enthalpy change around a closed cycle is zero. H is a state function. Here's an example, and we'll do more complex versions of Hess's law calculations in our mechanics lecture. We can go back to our melting, vaporization, and sublimation processes. And so the first line here is AS go to AL. That is the melting or fusion of a process, right? So delta H sub M, 0, is the enthalpy of formation of a liquid minus the enthalpy of formation of a solid. And then our second reaction is a liquid going to a gas. That looks like enthalpy of vaporization. So that's simply the enthalpy of formation of a gas minus the enthalpy of formation of a liquid. We can take those two reactions and add them together. So the solid goes to the liquid, then the liquid goes to the gas, so the overall process is solid going to gas. That's the sublimation energy, and that would be enthalpy of formation of the gas minus the enthalpy of formation of the solid form of A. Or we could write down simply enthalpy of fusion plus the enthalpy of vaporization gives us the enthalpy of sublimation. That is a Hess's law demonstration. When we're going to go calculate delta H for any process, we simply need to identify the process that's occurring, the target equation, the step whose delta H is unknown, and we need to take care and note the amounts, because if we balance a chemical equation different ways, which we know we can do that, we can do things as a multiple, then we'll get a different delta H overall. So the delta H has to be tied to a particular stoichiometry. Manipulate each equation with the known delta H values so that the target amount of each substance is on the correct side of the equation. That is the enthalpy of the products minus the enthalpy of the reactants, for example. We change the sign of delta H when we reverse a reaction or an equation. We multiply delta H by the factor of the amount of moles that we have. We can add the manipulated equations and the resulting delta H values to get the target equation. And we're going to do an example of this later on, I think, that will illustrate this nicely. Here's our standard enthalpies of formation again, and this shows us our last slide for this video, which is why we use enthalpy of products minus the enthalpy of reactants. You can visualize this as an energy state diagram. The green box is the reactants. We're on a vertical axis of enthalpy. If we decompose these into elements, then that's minus delta H of formation. If we reform products, then it's plus the delta H of formation for those guys. And we end up in our brown box products. So the enthalpy of formation of the products minus the enthalpy of formation of the reactants is the net transformation from our initial state to our final state. Next, we'll continue on with mechanics of Chapter 6, doing some example problems and calculations.